the web promises this really nice model, right? When you're on the web, you can go check your email, and you can go look at pictures of kittens, and you can go shopping. And the nice thing is that it doesn't matter what you click on. You can just use these things and interact with them. And if you click on a link that you didn't know what it meant and you ended up looking at something you didn't want to look at, well, that's okay. You can always, it might be unpleasant, but you can just click the close box and it goes away, and things go right back to how you left them with no effect on the other applications. Now, that's the promise, but despite this clean model, in practice, the web fails to deliver on this promise. It's still fraught with security vulnerabilities, right? I mean, there's buffer flow overflows and API vulnerabilities, and these things can compromise the browser itself and the host operating system. But even when the browser is correct, cross-site scripting, CSRF, and other flaws can mean that visiting a dangerous link, whoops, sorry, went too far forward there. Visiting a dangerous link might compromise your relationships with the other sites that you're interacting with. So, I mean, given all this complexity, what advice can I give my mom to stay safe out there when she's using the internet, right? I can say, be sure you practice safe surfing hygiene, right? What does that mean? Does that mean, don't click dangerous links? What's a dangerous link? I mean, can you explain that concept to an ordinary user? Or for that matter, can you even define it for me? Right? It's a dangerous link is the one that you clicked on and now your computer's owned. So I assert that these vulnerabilities aren't merely problems with the way that web browsers implement the API, but rather problems with the API itself. The web API has very complex execution semantics and subtle communications and sharing semantics, and this communication often occurs implicitly. Because these are problems with the API, they can't be fixed simply by re-architecting the browser that implements the API. The API itself needs to be changed. So for this talk, I'm going to explain why the API is broken. I'm going to offer a new API with simple execution semantics and explicit communication. And I'll explain how this new API can evolve without falling into the traps that befell the existing API. So that's where we're headed. So let me begin by motivating the need to change the API itself. So our community has been aware for some time that there are these flaws in the web, and we've been trying to fix browsers. But mostly we've attempted to fix it by trying to repair the browser itself. In other words, without breaking the API, without breaking the web or the existing applications. Projects like OP and iBoss refactor the monolithic browser into some clean modular units so that we can better reason about the responsibilities of each of them. Projects like Gazelle and Chrome refactor the browser's heap to separate pages into containers to contain faults. Now, both approaches have improved some classes of bugs, but ultimately, if we're not going to break the web, then the refactored browser still has to implement this standard and complex web API. So for example, if we want to support the implicit communications that are required by the web API, Chrome has to allow content from multiple sites to live inside the same process when it isolates things into processes. The adversarial isolation between the applications aren't much improved over what came before because the applications they're still ultimately constrained by what the API specification says about how they can interact. So no matter how much we rewrite the browser, there's still these complex interactions. And the premise of our project is that merely improving the browser implementation is doomed. Not because we're not great software engineers, but because the API itself is so complex that we can't even specify it correctly. So I'm arguing that the API itself is broken, and it's too wide and complex to ever specify completely and correctly. So how did it get that way, and what's going to keep us, even if we start over, from ending up there again? Well, what is the web API? What do HTML and CSS and JavaScript and DOM, what do they actually mean? Fundamentally, they're a protocol, right? They specify the semantics of a runtime environment. So some vendor writes a program and they post it up on a web server, and that program gets sent over the network, and it shows up at the client as this undifferentiated bag of bits. And the API is what defines the meaning of those bits. They turn them from a program from a static program into this running process. But this API that we've defined has been pulled in two opposite directions. This is why it's a disaster. On one hand, it specifies the behavior of the program when it arrives on the client. So let's call that thing a client execution interface, or a CEI, and I'll use that term repeatedly in the talk. We want this interface to be as simple as possible, right? We want to really understand its semantics so that we can implement them correctly. So if we really want isolation, we want this CEI to be minimal. But on the other hand, the web API has also been serving as a developer programming interface, and that's driven it to get fancier and fancier, right? We've been adding fancier graphics with transparency, moving graphics, fancier layout, fancier text, all this stuff we keep cramming into this developer programming interface. Developers want that programming interface to be as rich as possible so that they can build on top of it with just a little bit of CSS or JavaScript, and now they've got this exciting web application. So Clearly, these goals are at odds. This talk is about refactoring that API. We're going to separate these roles of client execution interface and developer programming interface. So in the existing API, the JavaScript serves as both the programming language and the execution model. And in the refactored world, developers can still program in JavaScript. That can still be the developer programming interface. But by the time that application arrives at the client, all the client sees and has to implement is a much lower level, simpler, and more enforceable model. This is the client execution interface. So while the client execution interface, or CEI, is minimal, we get to keep that fancy developer programming interface that developers love, and in fact, we can even make it even better. So you should have a certain skepticism, right? It's all well and good for a researcher to wander up onto the stage and say, oh, look, we started from a clean slate, and it's nice, and it's redefined, but who's to say that under evolutionary pressure, it's not going to grow into the same hideous complexity that we set out to address? Right? So we found an analogy that we found that very helpful in guiding this design as we've thought about this problem. This is sort of the underlying problem of rethinking this API. So let me share that design with you. So to give you an idea about this analogy, I'm going to start with a ridiculously impractical clean slate design. And then I will come back later and sort of repracticalize it. So we're going to start with the current arrangement of the web, where each vendor has a server somewhere out on the internet that it manages to handle its part of the computation. But instead of sending the code to the client, we're going to give each vendor another computer on which to render the client experience. So now we'll just connect the real client up with VNC, right? So now pixels go down to the client, keystrokes and clicks go back up to that client rendering computer, right? So this arrangement is very simple semantically. We can really see that the isolation semantics are strong, right? Because just like on the internet, right, the reason that the kitten site isn't too worried about Blobfish, even though they're connected with IP, is that if Blobfish sends a packet over the kitten site, well, it's just a packet. The kitten site, they manage their libraries, they choose their firewall settings, they decide what protocols they're going to operate on, and so they don't have to worry about random packets from the internet. They reason about them and they can protect themselves against it. Well, now the client interactions are following the same set of rules, right? So if the kitten site wants to send an attachment over to Hotmail with a fluffy little picture in it, well, that can occur from the client rendering computer to Hotmail's client rendering machine. And if it's going to go through, it'll work because those two sites share a protocol and they can communicate using that protocol. So the one component that everybody has to trust, which is this client down here, has really simple semantics. It's not trivial. We still need to reason about, for example, how the user knows which VNC window they're looking at. But the point is that the client is really simple. Richness and interaction among the web application grows and evolves out there on the internet somewhere without involving and adding complexity to the client. Now, my straw proposal was a lot ridiculous, right? Nobody actually wants to have, to open up their device and be connected by VNC to the rest of the internet. It would assume that the network is very reliable and high bandwidth and low latency, and there's plenty of extra resources around to do this computation, and none of these things are true. Well, let me point out an interesting trend. Increasingly, vendors aren't even bothering to maintain their own servers and data centers. Instead, they just rent out space at a multi-tenant data center, right? So there's Amazon or EC2 or Azure over there. And when Kittens moves into this multi-tenant data center right next door to the Blobfish site, it's not any scarier than it was when they were out on the internet, right? Because the Kitten site still selects and maintains all of its own protocols and libraries and software and firewall configuration. This works because the virtual machine interface that defines these multi-tenant data centers is a minimal and well-specified server execution interface. We can rely on it to have semantics that are equivalent to these sites operating independently out in the cloud somewhere, out in the internet somewhere. Okay, so let's bring back those strawman client rendering machines, and we'll build a little tiny multi-tenant data center right next to every client. And then when we want to take these, when vendors want to run their client rendering software, we're going to push that down to that little multi-tenant data center right next to the display. So we'll call this thing a Pico data center. So this solves the problem with the strawman because now the user interface connectivity doesn't depend on the network. But just as importantly, just like the case where the servers moved into the multi-tenant server data center, we didn't give up anything about the secure autonomous interaction model of separated internet servers. So again, for this to work, our little Pico data center needs to have a minimal client execution interface. So this analogy has worked really well to help us reason about these interactions. We'll come back to that idea in a moment. But first I want to answer the question of how big does a client execution interface have to be to replace the web? And the answer is not very. I'll show you the entire interface here. First, just like a cloud virtual machine, we need some way to execute code. In our case, we're going to allow binary code, that'll be important in a moment, that lives in one address space, has memory allocations, threads, and a synchronization primitive. Just like in a cloud virtual machine, the only way that these applications can communicate with the world or with other tenants that happen to be next door in this little Pico data center is the Internet Protocol, is IP. So this, again, appeals to that notion. It brings down that notion that each of these vendors is as independent as they would be if they're out on the Internet. Just as in the straw proposal, we need a minimal interface for painting pixels and getting key clicks back. And that trusted UI has to be slightly more than trivial because, again, we have to reason about things like helping the user understand which screen they're looking at. And finally, because the only primitive we gave the client is IP, we provide a couple of crypto primitives so that applications can provide for themselves privacy and integrity properties. Notice that I didn't say anything about TCP, much less HTTP and MIME types. There's nothing about font rendering, much less cascading style sheets. There's nothing in the CEI about malloc or structs, much less JavaScript objects. So this interface is really minimal. Okay, so maybe I can make some OS nerds get all excited about the simplicity of this, but are web developers really going to be willing to write applications in assembly and paint each individual pixel on the screen? I mean, that's a little 1980s. No, I mean, clearly, we need to keep the developer programming interface rich and evolving to capture this benefit that the web has. So that's why we chose binary code as the core of the client execution interface. That little client-side data center accepts any binary program from the vendor, including, for example, a WebKit browser, which is what we experimented with the most. So now HTML, cascading style sheets, JavaScript, MIME, and HTTP, all that stuff is part of the application client, just as Python and MySQL are part of the application server. So none of this stuff is inherent to the client definition itself. This is a big advantage of separating the DPI from the CEI. The web developer can use any HTML renderer that she wants, and she doesn't have to be compatible with all of them. If her content renders nicely on Firefox, then that's fine. That's the renderer that she'll send. Of course, once the vendor has the freedom to install any binary program in that client Pico data center, why stop at HTML? I mean, if you want to use GNOME libraries and run GIMP or Inkscape, you can do that. If you want to use KDE and have this spinning 3D globe, you can do that. And if you want your 8-bit graphics, we can do that too. I guess it looks just like a black box, but there's some pixels in there. So these are all screenshots of real applications that run in embassies. So the model I've described explains how we can bundle up the browser's CSS and HTML renderers and let it render away in this isolated container. And truth be told, in our experience, 90% of the browser's behavior is really just about rendering. But for this story to make sense, we have to consider that very interesting other 10% of the browser. What happens to all of the browser facilities for client-side communication, right? This is where a bunch of that complexity comes from. What about things like form submissions, cookies, clicking a link, and clicking the back button? In each case, today's browser helpfully provides some implicit communication between mutually distrusting applications. So we could try to put all this stuff back by adding some calls into the client interface to support it, but then that's going to lead to a couple of problems. First, the web API doesn't cleanly separate communication out from the rest of the API, right? It's difficult to talk about DOM communication without defining the whole DOM. And second, as a result of this first problem, if we head down this path, we're going to lead to adding growth and complexity back into our client execution interface, which is what we set out to avoid. So if we can't have applications communicating through a shared rich platform, then how does it occur? Well, let's go back to that Pico data center analogy. If we wanted to have, if these things really were out in the cloud just talking by VNC, how would those independent servers talk to each other? And the answer is, well, they're going to use protocols to talk to each other. So let's think about how we would replace each of these implicit interactions with a protocol. So let's say the Kitten site wants to send a filled out form to Hotmail and have it be authenticated as the user. In today's web, that can happen implicitly, where the Kitten site just posts up an HTML form and the browser helpfully posts that form off to Hotmail's server, implicitly including cookie information that authenticates the user along the way. And all of this implicit stuff was very helpful in 1993, but it's led to all kinds of mischief such as cross-site request forgery because of this implicit behavior. So in the embassies model, we ask, well, what would this look like with a protocol? There's no such implicit behavior because that's not even specified in the client interface. So what happens is the Kitten site can just show up to the Hotmail client with an IP packet and send it a protocol message and say, this is what I'd like to do. And if Hotmail chooses to speak that protocol and it authenticates the request, then it can make an authenticated request back to its backend server. Let me give you another example. How do we color visited links purple? right? Today, this is handled implicitly in browsers. And again, this seemed like a good idea when all we had was HTML. But since then, it's led to these history leaks because the other sites can discover things about using their imperative code about where you've been. If we want this to be a protocol, we can recreate this interaction. We can say every time we visit a link, like we're on the Kitten site and we go to the Tabby's page, we should forward that event via a protocol on up to some central repository. And then he can relay it on into any other application so that he can color the link purple too. We can recreate that whole interaction. But why would we want to, right? Maybe that's not a good idea, right? I mean, this maybe isn't a communication pattern that we want to reproduce. Refactoring these interactions into explicit protocols makes it more obvious that some of the design decisions that we made in the depths of this complex browser might have been bad ideas. And when we look at them under the harsh light of a protocol spec and as an RFC, maybe that's not such a good idea. But it also gives us the opportunity to fix them, right? The Kitten site could say, well, I think I'll just keep my history to myself, and effectively I'll color the links in the edges in the link graph purple rather than the nodes. So the idea is that in the refactored world, clients arbitrate every interaction that they share with other applications, just as their server code decides what protocols it's going to speak. So the client code can reproduce any interaction, but it also, if a protocol is a bad idea, they can change or simply reject their interaction with it. So another example here, what does it mean to click on a link that leaves a website? So in today's browser, that's, again, an implicit interaction. The browser does all of this implicit stuff like parsing URLs and processing HTTP and so on. In the protocol model, on the other hand, we have to ask what clicking a link means. So again, think back to that VNC model. It means the Kitten site has control over part of the display and is yielding that control over the display window off to the Puppy's site. So in this example, we've got Kittens handing off a capability in a protocol message over to Puppies. Now, it's clearly OK for the Kitten site to know where the user's going, so it can send that capability. But is it necessary for the Puppy site to know what URL the user came from? Well, if we want a back button, we need some way to send a message back to the Kitten site. So we show in the paper how you can let the Puppy site restore the Kittens page without knowing which specific page on the site that the user came from. And if even that's too much, we could shield the identity of the outbound site using a trusted intermediary. And this gets even a little bit more complicated when we go to dealing with things like tabs, who paints the tab, and who gets to see what on the tabs. But the important point is that what's great about this is that the protocol model, when you think about things as protocols, these ramifications of introducing communication between the vendors, which we had been doing implicitly, all comes to the surface. We understand, we can reason about these ramifications, and vendors can correct them, and we can evolve new and better protocols with better properties. So you might be concerned about a very different problem with our client-side data center model. Today, when you visit a new site, almost all the heavy machinery that the site needs, the monolithic browser, is already loaded and running on the client. And the site just sends down the little bit of extra content that makes that site special, a little bit of JavaScript or something. So what happens when instead of a modest application running on top of a huge rendering stack, we have a little tiny client, and each application brings with it a big stack of rendering and interaction machinery? Isn't that going to be prohibitively expensive? Well, we don't think so. So here's the intuition. Think about on the server side, vendors do have complete freedom to diverge from each other and configure and tweak their own software stacks however they want. In fact, that's the advantage we're trying to capture. But even though they have that freedom, the common case is that there are a few popular stacks that are well maintained, and vendors choose from among those and then push the evolution of those stacks from there. So we expect that a similar thing is going to occur on the client. Vendors are going to can choose any software they want, but the common case is that most apps are going to consistently select components from one of a few well-supported stacks. And that means that caching is going to be effective. So if you buy that intuition, then we can now revisit our client-side Pico data center. We'll zoom in there. Now, maybe the Kitten application shows up running on GTK and GNOME and X Windows, and Hotmail shows up running on a Windows stack. Now, when another site shows up running on a similar stack, there's no reason that it can't use the same bits that already arrived for the Kitten site. So, in fact, we can have all the applications fetch their bits through a common application, caching application. And the great thing is that this cache process is completely untrusted. Right? We don't have to trust that cache. The application knows what bits they're expecting, and they can verify that the bits have the right fingerprint when they're finally delivered into the applications container. So the cool thing here is we've kept the CEI really simple, right? We got back all this caching performance, but we don't have to depend on the client to actually implement any of it. So things like the browser's object cache and the operating system buffer cache we're replacing with untrusted components. So does it work? Well, in the paper, we measure how long it takes to launch some popular sites in an already open WebKit browser under Linux. And then if we launch those same sites from a hot cache in Embassies, it adds a couple hundred milliseconds to shift things around and check in memory and check the hashes. And this is even though in each case we're launching a nearly 80 megabyte browser image from this untrusted cache. Now, if the cache is warm and not hot, that is, it doesn't have exactly the right bits but has a similar application already loaded, then the launch time is similar. So essentially, we've claimed that benefit of the browser object cache and the operating system buffer cache, but without putting them into the TCB. So you might reasonably be saying, wow, 200 milliseconds, that sounds horrific. But let me make 3 points about this performance. The first is that we're only adding that cost when the user crosses over into a new site. So within a site, you can use HTTP and it'll go as fast as you like, or you can use Speedy, or you can use the thing that hasn't even been invented yet because you control your software stack on the client, so you control its relationship with the server. Second, these measurements are based on loading the entire default WebKit. It ignores even simple startup latency optimizations because that WebKit wasn't designed to be used this way. Most importantly, I'd like to point out that what we've done here is we've exchanged a persistent problem of confusing and subtle web semantics for a modest performance problem. Right? This is a good trade-off. This is the order we should be solving the problems because the performance problem is something I know we can measure and then hit out of the park. So let's come back to these security problems that I'm claiming this approach helps us solve. How does refactoring fix specific security problems? Well, let's go back to the link coloring example. Embassy's refactoring doesn't inherently fix this problem, but what it does is it does two things. It makes the consequences of these interactions much more obvious in the form of protocols. And second, it puts vendors in a position to adopt a repair outright. In contrast, every time we fix a bug in the monolithic browser, we have to get together in the IETF and change a globally deployed platform, and we have to find a compromise design that doesn't break the existing web. Let me give you another good example, cross-site scripting. So in cross-site scripting, an attacker sends some crafty comment up to a site, and the site passes it along to another client. And the intention of the site is that comment will appear like in this little green region down here. But the attacker has cleverly escaped its container. They've put in some funny escape codes that trick the browser, exploiting this complexity in the API. And now the attacker is running with the application's authority. So the structure of this attack should sound pretty familiar. It's just like SQL injection on the server, where little Bobby Tables shows up on the server side, and he doesn't get escaped properly, so now the attacker's code is running with the authority of the SQL application. So with our Pico data center analogy, we can always ask the question about the client-side problem, how do we solve that corresponding problem if it's out in the server? Because abstractly, that's exactly the way our clients are set up now. Well, what happens on the server? The vendor patches up its software stack. It tosses out its crummy Perl script that they wrote in the summer, and they start using a better SQL library with good input data escaping and perhaps even some taint checking. So the vendor can fix its bugs, its server code, at any point in the software stack and can deploy the fix whenever it wants to. So let's go back to the client side. We can't do exactly the same thing on today's client because even though a vendor can patch its JavaScript and its HTML, the libraries and mechanisms for nesting rendered content is kind of where this problem's coming from. Things like HTML and the DOM, those are all determined by the browser. So not only does the application writer get no choice in the matter, but he has to be sure that whatever confinement mechanism that he writes is correct for every browser that the code's going to run on. In the refactored web, the vendor can apply a patch wherever it's needed, wherever in the stack that it's needed. So for example, going back to the cross-site request forgery example, cross-site scripting example, a rendering stack could come along and offer an improved frame or div abstraction designed just to solve this problem, and the vendor can adopt it right away, fixing the flaw immediately without waiting for IETF consensus and a browser change. Just as on the server, better mechanisms can evolve and be rapidly deployed. So the main points I want you to take away from this work are these. First, the web API is poorly specified because it's conflating these roles of client execution interface and developer programming interface. Second, that client execution interface needs to be minimal if we want to get isolation to work. Third, if it also admits native code, then we can still have those rich DPIs. In fact, the exact ones we have on the web today and more. Now, those two concepts are tightly coupled because supporting rich DPIs is what relieves the pressure to add richness down into the client execution interface. Fourth, shifting the developer programming interface into vendor-supplied code sounds like it might be expensive, but it's actually not so bad, and we'll happily accept a performance problem that we know how to make measurable progress on in trade for making significant progress on these security relationships. And finally, correct isolation isn't the whole story. We have to understand how we're going to replace the violations of isolation, the cross-application communications that we're eliminating along with the browser. So the Pico data center is a really useful analogy for this because it guides us. It appeals to how we've solved this problem out on the internet by talking about how we use protocols and how those protocols expose the trade-offs when we enter a relationship with other vendors. So our vision then is that we're hoping this approach can help us deliver the promise on the web and remove the inherent peril with clicking on a link. All right, that's what I have. I'm sorry, that sounds like a challenging question. I have to catch a flight.
Thank you, Borisov, University of Illinois. So this is very interesting. There seems to be a lot of similarity between doing this and what's happening on a mobile platform where every single website I visit develops their own app that I now have to install. So how do you see that convergence being? Do you see the two models eventually being one and the same?
I think there definitely is convergence there. I think what we've got in the mobile world right now is we're pushing toward the right user model. Users expect these sites to be more inherently independent and to have more restricted interactions among them. But I don't think we're exploiting all the opportunity of that user model because the mobile applications don't depend on a clean and narrow execution interface, which they are much closer to being able to actually exploit now.
Hi, excellent talk. Jude Nelson, Princeton University. Could you comment on the effectiveness of web indexing in this new scheme? Instead of having a document-oriented model for my web applications, I instead have this binary-oriented model. Do you think it will make the job of Google or Bing or Yahoo much harder to keep track of the content on pages?
It's a perfectly reasonable thing to be worried about. Here's why I don't think it will be. So I gave you this intuition of why I think caching is going to work, which is that I think even though vendors can go any way they want, the common case is they're going to use one of a few popular stacks. So that's likely to be true. It probably won't be just HTML anymore. Maybe we'll see a resurgence of Java or something else like that. And so, but the result is that means that the common case is that vendors are actually going to still be using one of a few popular transit protocols. So maybe we'll still see vendors using between their server and client pieces JSON or maybe RMI from Java. But I think the idea is that vendors will still expose interactions that we'll be able to sniff on.
Lakshmi, NYU. Do you agree with the fact that we are actually caught at a time when there is a disconnect between how the web browser is designed and how web pages are designed, and how web pages are actually being misused? So the very fact that I have to download 100 objects to download a single web page, and there is a whole 7 layers of parsing, and even just trying to understand the structure of how content is placed in a web page sounds weird. So in essence, if I have to take your work in a different way, is there an interesting problem where how should web pages itself be designed?
One way you can read this work then, I guess, is that one way you can look at it is to say, why is, when a web developer sets out to design a web page, why is the contract that they're going to sit on top of a tall stack of software no matter what. They need a rich developer programming interface. And so there's going to be some tall stack of software of some shape or another. And what this work is asking is, why is a bunch of that stack specified in a wide-reaching contract that includes all of the client machines, as opposed to just letting the developer decide which stack they want, and let another developer say, oh, maybe we're going to, instead of using that stack, we're going to use a Python-based stack and hang out with that community. So, I think that it's inescapable that there's going to be a bunch of complexity under the developers, from the top of the developer programming interface, because that's what web developers want. But we want to put that complexity and the choice of which complexity in the hands of the web developer.
Probably there's a much longer discussion.
Let's have it outside.
Yeah.
That's good.
Okay.
Okay. Okay. Let's thank the speaker again. Thank you.